Problem 1.76. In this problem, an sled shown in the figure below slides along a thin horizontal layer of water between the ice and the runners. The horizontal force of the water puts on the runner is equal to 1.2 pounds when the sled's speed is equal to 50 feet per second. The total area of both the runners in contact with the water is 0.08 feet square, and the viscosity of the water is equal to 3.5 times 10 to the fifth pounds per second per meter square. What we would like to determine is the thickness of the water layer under the runners. Assume linear velocity distribution in the water layer. As the problem indicated, we're going to treat the velocity to be linear, so that's one of the assumptions. We're also going to say that the system is under steady state conditions, and we treat water to be a Newtonian fluid. Okay, so since we're dealing with forces, let's try to do a free body diagram so that we could see what we have. So this is going to be representation of the sled, right? It has, so this is the ice layer that is at the bottom, and we are located at a distance b from that ice. This fluid has a viscosity mu. We also were given that this moves at a certain velocity, right? And it was also given us that a horizontal force that the water puts in the runners is going to be equal, so the force is going to be equal. So it's a horizontal force that we have over here. Okay? So the information that we have is, so if we relate that the amount of force divided by the area, and since the force and the area are parallel to each other, this is going to be a shear stress that takes place. So notice that this is basically a relationship of force between the runners and the water. At the same time, we know that the shear stress created by the water is proportional to the viscosity and to the rate of shear strain of the fluid. Okay? So since we already know that the velocity is going to be linear, so we're going to define the velocity linearly to be v y over b. Once again, we evaluated at y equal to 0, and this should give you 0 to maintain the non-slip boundary condition, and at y equal to b, the velocity will give you v, which is the velocity of the sled. We take the derivative of this with respect to y, and this gives us v over b. So now we're going to relate this to quantity. We're going to replace this so that tau is equal to mu velocity divided by v. And we're going to join these two equations and make them equal to each other. Okay, so the force divided by the area is equal to mu velocity divided by b. Okay, and we have all the information, and what we're looking for is b. So b becomes simply mu v force times the area. Okay, so that's the relationship to calculate the distance b, which is the space between the sled and the ice. Okay, we're going to substitute all these values. Please make sure that you double check your units, and your value should be equal to 11.7 times 10 to the negative 4 feet. This is a reasonable value. Notice that we don't want to have extremely large distance between the sled and the ice. And this number is small enough and reasonable enough for our calculations.